Hi everyone. So we're going to start looking at the simplex algorithm today. So the simplex algorithm is an extension of linear programming that you've already studied. So it's still in D1, but it's part of the full A-level course, and it's not in the AS. The simplex algorithm, well, when we're doing linear programming so far, you've been doing it graphically. You've been maximizing or minimizing objective functions using a graph, and that obviously limits you to just having two variables because you can only plot a graph in 2 dimensions on a piece of paper in an exam. So the simplex algorithm, it's basically just gets rid of that problem for us. So it helps us to solve, just dropped my calculator, helps us to solve linear programming problems with more than two variables. It does it algebraically, so it works in a table, which we'll see later, not graphically. So obviously, algebraically, you can have more than two variables, and it's an iterative process. So it kind of seeks to solve the objective function. So what we're going to do today is I'm going to introduce it using a 2D problem, so just with two variables. So we're going to solve a problem using linear programming, doing it graphically to start with, and then we're going to use the simplex method to solve the same problem, and hopefully it will help you see how the simplex algorithm works when we refer back to our graph. Okay, so the first thing I'd like you to do is here is a linear programming problem, and what I'd like you to do is to draw a graph. Okay, so I want you to maximize p equals 3x plus 2y, subject to 3x plus y is less than or equal to 9, and 2x plus 3y is less than or equal to 12, and you've got your non-negativity constraints there as well. So I want you to do it graphically. That's really, really important. And I also want you to use points testing. So I want you to write the coordinates of each of the vertices of the feasible region, okay? And then I want you to work out the value of the objective function at each of those vertices, all right? So pause the video, and when you unpause it, I'll show you my answer to that, okay? Okay, so I'll show you my graph. Okay, so this is my graph for it, and this is the feasible region here, and each of the vertices, so there's 0 0 at 0 0 p, which is 3x plus 2y, is 0, at 3 0 p equals 9, at 0 4 p equals 8, and this one 15 over 7 and 18 over 7, p is 81 over 7, so that's 11 point something, isn't it? So that's the maximum one. Okay, so p is maximized at that point. If you were to have drawn an objective line in, you would have kind of gone up and found that it hits that point last. Okay, but I specifically wanted you to use points testing so that we can refer back to these later. Okay. So we're going to now think about setting up this problem as a simplex problem and then putting it into a table. Right, so this is our original linear programming problem, and we're going to turn it into a simplex problem over here. Now, in order to do that, we need to add in something called slack variables. So the best, well, I'll explain what a slack variable is first. So it might be that when you maximize the function, when you solve the problem, that actually there's a bit of leftover. So the best analogy I've seen for this is imagine that you had a 20-meter roll of cloth, okay, and trousers took 3 meters to make, and I don't know, a skirt took 2 meters. to make. Okay, so that's how much material each of them took, and you had 20 meters to use altogether. Now, it might be that you chose to make 2 pairs of trousers and 3 skirts, and then you'd have this 8 meters left over in your 20-meter roll of fabric. And whatever the leftover is the slack. So obviously we're trying to minimize that slack in this one. So we'd want to make more of each. And we'd also, but it might be that it's to do with costs. So you might not be able to use all of the material. So you're always going to have, you might end up with a little bit of leftover stuff. And that is the slack variable that we're putting into this problem. Now, the other thing to point out is the simplex algorithm only works when you have less than or equal to constraints. So we will deal with, in a couple of lessons' time, something called the 2-stage simplex method, where you basically just do it twice. And that deals with when some of the constraints aren't less than or equal to. But for now, our problems have to have less than or equal to constraints. And also, sometimes you get an objective function written without the p equals or whatever letter equals. I find it really, really helpful to put the p equals in to this, just because it helps me remember how to set it up properly. So you would never lose marks for adding that in. It's just, I find that really helpful. So here, because we've got 2 constraints that aren't our non-negativity constraints, we're going to add in 2 slack variables. Okay, so the first thing here is I just need to adjust my objective function. So we're always going to want to have a constant on the right hand side to set up our simplex tableau or our simplex table. So we'd want to write that as p minus 3x minus 2y equals 0. So that's called our objective function, and that's going to go in something called the objective row of our table. Okay, and it's going to be subject to, and then we need to add 1 slack variable into this constraint. So what we're doing is essentially making it, changing it from an inequality to an equality. So we're making that, putting that extra bit in so that we're using the whole 20 meters, or putting that extra bit in here so we're using the whole 9. We'll have 3x plus y plus s1. So that's my slack variable 1 equals 9. I think in the book they use like P, Q, and R, or R, S, and T. It doesn't matter at all. In exams, mark schemes, they sometimes use S1, S2, and S3. So our second one is going to be 2x plus 3y plus S2. So that doesn't, it's going to be a different number, equals 12. Okay. And then I've got my x is greater than 0, y is greater than or equal to 0, and also my slack variables have to be greater than or equal to 0. You can't have negative leftovers because we've only got a limited amount of materials. Okay, so that is our linear programming problem changed into a simplex problem, so that we can now put this into a simplex tableau. Okay, so I'm just going to pause the video and draw some tables. I think we need 3 tables. I did it earlier. I think we need 3 tables for this problem. So I'll do that, show you what they look like, and give you a chance to draw them. Okay, so your tables should look like this. This is what they'll look like in the exam. They'll be given to you in the exam. The left-hand column will have, it's got something called the basic variable, which I'll explain later. And I've just put BB for later down. It's fine to abbreviate that. Then you need a column for each of your variables. So X, Y, S1, and S2 in this problem. A column called value. Sometimes that's called right-hand side or RHS. and it just means it's the number, the constant on the right hand side of the equation, of the equations up here. The ratio, which we'll come on to later, that's something that we have to work out in order to do the simplex algorithm. And then row operations, and that's something that we have to, it's just useful to write down in the exam. So we add a little column on the right hand side so that we know what we're doing, because otherwise, once you've got a bigger problem, this can get quite messy otherwise. Okay, so to fill in your simplex table, your first one, we have you put the subject of the constraints at the top, and then you have the objective function at the bottom. Okay, in Edexcel, that's important. That's how they're set up in the exam. It's not always the case in other exam boards. So if we ever end up doing any exam questions from different exam boards, the tables might look slightly different, but by then you'll be used to it, so it's okay. Okay, so our first constraint, we have 3x and 1y and 1 S1, no S2s, and the value, the right hand side, is 9. Okay, we'll come back to this later. The second constraint, we have 2x, 3y, no S1s, 1 S2, and the right hand side is 12. And then the objective function, we've got minus 3x, we've got minus 2y, no S1s, no S2s, and the right hand side of the equation is 0. So what we're essentially doing here is we're setting up some simultaneous equations in a table to be solved in pairs. Okay, now the basic variable is the next thing. Now the simplex method, it starts at the origin. So let me find my graph. If we go back to the graph, it starts down here. Okay, so when x and y is 0. So the basic variable is the only variable that's non-negative, basically, in each thing. So at the start, when x is 0 and y is 0, for this row, the basic variable is S1. For this one, if x is obviously at the start, x and y are 0, it's S2. And for this one, it's P. Okay. Right, I'm going to stop this video here. So we've got our initial simplex tableau set up. So that feels like a good point to stop. And I'm going to start the next video here, so we go through the whole method, because it feels like it's quite a long time. So just check you understand everything up to there and how to set it up, or you can follow it at least, maybe not do it yourself. And then we will go through a simplex algorithm completely.